In this problem, we have this company that's manufacturing cans, metal cans, and they want the volume of the cans to be 250 centimeters cubed. They tell us the cost for the two circular ends of the can is this number, and the cost for the sides is this number, and that's per centimeter squared. So we want to find what dimensions will minimize the cost. So in this case, the cost of the can is our objective function. So we need to first come up with a function that represents the cost of the can. So the cost of the can will just equal the cost of to make the top and the bottom, the two circular ends, and then the cost of the side piece. To figure out what that cost is going to equal, we just need to take the price per square centimeter and multiply it by the total area that we need. So the cost of the top and bottom is just going to be the price per square centimeter for the top and bottom times the area. And then same thing for the side, so the cost per square centimeter for the side times the area of the side. So now we just need to figure out what the area of the top and bottom is going to be and what the area of the side is going to be. So looking at this diagram over here, we take our can and we break it down into the top and the bottom and then the side piece. Now the side piece, if you roll it up, it's circular, or it's like if it's the cylinder side, but if you unroll it, basically it becomes into a rectangle. Now looking at the rectangle, which constitutes our side piece, this dimension of the rectangle is going to be the circumference of the circles that constitute the top and the bottom of the can. And then this dimension of the rectangle is just going to be the height of the can. Now you can recall that the formula for the circumference of a circle is just 2 pi r. So we have the length is 2 pi r, and the height we'll just use h to represent. So we know the area of a rectangle is just length times width. So substituting the values for the length and the width, we get the area of the rectangle, or the side piece, is 2 pi r times h. Now let's look at the area of the top and the bottom. Well, those are just circles, so we can use the formula for the area of a circle, which is pi r squared. But remember, we have two of these circles. We have two circles with area pi r squared because we have the top circle and the bottom circle. So then the area of the top and the bottom is 2 times pi r squared, and the area of the side is 2 pi r times h. Okay, so now we're getting somewhere with our cost function. But you can see that the cost function currently has two variables. So really I should write my function name like this. My cost function is a function of two variables, the variable r and variable h. But we want to get it down to just one variable. So to do that, we're going to have to use some additional information from the problem so that we can relate r and h together somehow. Well, the additional information that we need to use is that the volume of the can needs to be 250 centimeters cubed. So we know the volume needs to equal 250. Now we need to use the formula for the volume of a cylinder to relate the variables r and h. So if you remember, the volume of a cylinder is just pi r squared times h. So now we get 250 equals pi r squared times h. So this formula allows us to relate h and r, and we can express one in terms of the other. So what we'll do is solve for h in terms of r, and then we can substitute that value of h into our cost function. So we can get our cost function down to just one variable. So solving this volume formula for h, we get that h equals 250 divided by pi r squared. So now let's take that value of h and plug it into our cost function. And when I plug that in for h, now I can simplify this a little bit. And so I'll just get 0.0015 times 500 over r. So now I have my cost function as just a function of r. So I can call the function c of r now because it just depends on one variable. Now let me clean this up a little bit by multiplying these constants together. And so I just get this for my cost function. Now let's think about the domain. We just need r to be strictly positive. So our domain is this open interval from 0 to infinity for the value of r. So now we need to find the critical values, so we take the derivative of the cost function, and so we get this as our derivative. Now remember, pi is just a constant. So when we're taking the derivative of this part, it's just 2 times 0.016, which gives us 0.0032, and then we still have that multiplied by the pi, and then the r goes to the first power. Now we need to find the critical values, so of course that's where the derivative is not defined, or where the derivative equals 0. Now the derivative wouldn't be defined when r equals 0, because I'm going to have division by 0 right here, but 0 is not in the domain. So the derivative will be defined for all the values of r that are in the domain. So we just need to find out where the derivative equals 0. So we need to solve this equation now. So we find that r equals the cube root of this. Plugging that into our calculator, we find that r is approximately 4.21. So this is the critical value. Now it's the only critical value, so when we do the second derivative test, if we get a conclusive result, we'll know that we have an absolute max or an absolute min, depending on the value of the second derivative. So let's find the second derivative and then plug the critical value into the second derivative. So I found the second derivative. Now let's take the value of r and plug that into the second derivative and see if it's positive or negative. So I plugged that in. I plugged 4.21 into my second derivative, and I get this, and I can plug that into my calculator, but all I really care about is whether it's positive or negative, and I know this is going to be positive because all the numbers here are positive, and I'm adding them together. So we know this is positive, which tells us we have an absolute minimum when r equals 4.21. And r in this case is measured in centimeters, so when r equals 4.21 centimeters, that's when we'll have the smallest cost for producing the can. So the dimensions that minimize the cost of the can will be a radius r of 4.21 centimeters and a height of 250 divided by pi times 4.21 squared, which is approximately 4.49 centimeters. So those are the dimensions that will minimize the cost of the can, and in this minimal cost we can find by taking the value of r and plugging it into our cost function. So the minimal cost is about 26 cents per can, and we get that cost if we use these dimensions.